Welcome everyone to Introduction to Energy Systems, our first seminar, What is an Energy System Anyway? This is a first in a series of 6 webinars from the Energy Systems Signature Area at the University of Alberta. In this series, each seminar will build on topics of the previous sessions to give participants a more complete picture of energy systems and our current transition to a low hydrocarbon future. We will emphasize a multidisciplinary approach, focusing on technologies and processes, environmental and societal impacts and their mitigation, ethical considerations, and how energy systems integrate into our daily lives. This series is designed to help guide your awareness on the complex web of technologies, politics, economics, and environmental and social considerations affecting the energy transition. My name is Amina Hussein, and I'm happy to be the moderator for this webinar today. I'm an assistant professor in the Department of Electrical Computer Engineering, where I work in plasma physics. My team develops laser-based probes for agriculture and land reclamation, and we study the physics related to fusion energy systems. My pronouns are she, her, and if you can see in my Zoom name, I also invite you to add your pronouns as well. We'll begin our webinar today by respectfully acknowledging that the University of Alberta is located on Treaty 6 territory, a traditional gathering place for diverse Indigenous people, including the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Inuit, and many others whose histories, languages, and cultures continue to influence our vibrant community. As we explore energy systems, we acknowledge the territories, communities, and peoples that have been essential partners in this research. We are truly grateful to have the opportunity to work, study, and live on this land. So in our first webinar in the series today, we will be answering the question, what is an energy system anyway? A system is a set of interconnected components that work together to perform a particular task. For example, our bodies are composed of cells, organs, and the connections between them that all lead to our experience as living, thinking beings, with the results being much greater than its parts. Here, we are exploring the behavior of an energy system, asking questions about the parts and connections that will cause a system to behave the way it does and how we can influence them. We'll build up from small-scale systems that could be in your home to large-scale global systems and discuss how energy extraction, processing, and use affects the world around us. The life cycles of various components and the diversity of Indigenous perspectives that are essential to their operation will also be discussed. To help answer this question today, we have 4 esteemed speakers from the University of Alberta. They are Dr. Andrew Leach, Associate Professor in the Alberta School of Business, Jessica Vandenberghe, Indigenous Engineering Industrial Professor and Associate Dean of Engineering, Community and Culture, Dr. Pierre Mertiny, Professor of Mechanical Engineering and Associate Dean of Student Conduct, Dr. Evan Davies, Professor of Civil and Environmental Engineering. In our webinar, each speaker will give a 15-minute presentation. After these 4 presentations, we will open the panel to audience questions. So you can see on Zoom that there's a Q&A box, and you're welcome to submit your questions on Zoom throughout the session and also to direct them to any of the speakers. The Zoom chat is also available for you to discuss amongst yourself, share thoughts, or ask about any technical challenges that you might be having. Please be sure to stick around at the end of our 4 presentations and then panel discussion to take a survey, which is aimed at understanding what you might like to see offered in the future after this webinar series. This information will also be used to help us develop an energy systems curriculum. So we're excited to present today's session and encourage you to sign up for future webinars, which will be posted on the Future Energy Systems and Energy Systems Signature Area websites as soon as they are available. All right, so getting started, our first speaker is Dr. Andrew Leach, who will be speaking to us about the nerd value of solar power. Andrew Leach, pronouns he, him, is an economist working on climate change and energy policies. Outside of work hours, his 2 kids, cycling, and arguing on Twitter keep him busy. So please go ahead, Andrew. We're looking forward to your presentation.
I have to be the stereotypical, Andrew, you're on mute. So thanks, everybody. Thanks, Amina. Thanks, Future Energy Systems, for welcoming me for this. And apologies if I'm a little bit frazzled. My computer decided to lock me out over the last half hour, and I just managed to get back in. So what I want to talk to you about today is a relatively small energy system. As Amina said, can be anything from the size of your house to the global energy market. And I'm going to tell you about a particular part of mine which is my energy system, which is the solar power system that we have on our house at home, and a little bit about why we added it, how it works, how much it costs, how do we get paid, how much do we make from it, and then eventually I hope answer some questions that you might have about it. So the first question that most people have is, what is it? So this is an install picture of our solar power system. It's on our garage. It's 7.6 kilowatts installed capacity. It's south facing, and we basically are able to live most of the year without tree shading. Shoulder season, we get some interference from trees from our neighbors. And we had the advantage of having a garage that was purpose built for a solar array installed. And I tracked data with two systems, a Nurio and an AP systems monitor, that let me download a whole bunch of information from it, which is related to the nerd value that we're going to talk about. So why did this happen? Why did we end up with solar? Why did we want to change our interaction with the electricity utility? Basically, this is my students' fault. I used to run an assignment in my class when I taught our Buick 463 and 563 classes in the business school to ask them to evaluate financially a solar power system for my house. And I'd give them all of the information in my house. I'd give them an up-to-date quote, and I'd send them out to learn about the solar market, how it works. And basically every year that they do this, they'd reliably come back and say, no, sorry, it just doesn't make financial sense. Even if you factor in Alberta had a carbon price at the time, etc. And even with that all factored in, it didn't make the grade. But then in 2017, one of the groups came to me and said, they gave their presentation and they said, yeah, it only returns you maybe 1%, not even. You'd be better off to lump down on your mortgage if all you care about is the electricity. But they said, if this would generate a cup of coffee a day of nerd value for you, and we think it would, it's the equivalent of a 20% rate of return. And so they knew me well enough that, here we go. And essentially I arrived home and had to inform my family that we were now going to spend $13,230 on a solar power system because of the excellent presentation that my students had given me in class. Now, that was only part of the cost of the system. We did have some rebate when we put it in from Energy Efficiency Alberta that covered a little bit of or a substantial proportion, 30% of the cost. And so now we're essentially taking a big bet on a larger energy system, which is Alberta's power market, because our return on that $13,230 is going to depend on what happens with electricity prices, contracts, and a little bit about how our market works overall. And so let's start with some basics. How much does it generate? So these are my annual average curves, just so you get a sense of, November, December, January, and February tend to be terrible because of low sun angle and because of snow cover. And May, June, and July are great in terms of generating solar power. But these are averages. There's a whole bunch of variation in between. So we have sunny days. These are hourly data, so they're a little choppy, but it just makes the graphs a little bit easier to generate. And so again, you have good years, good days, bad days. It's quite variable. And so most of the year, it does what you'd predict. It produces power, more than enough power to power our house in the middle of the day, even sometimes in November, December, January, and February, although not very often, not very many hours. And in the summer, we produce a whole lot of extra power. And in the winter, we produce, on average, very little. So we have a seasonal issue. And of course, again, this varies a lot from day to day and from hour to hour as well. But what you really care about, I guess if you're me and you're an economist, is how does this actually show up on my bill? And so our solar powers provide energy. Think of our house as having first call on that energy. So before it goes anywhere, if we can use it, we will, and our house will prioritize using solar. But if there's extra energy either required by our house or generated by our house, either way, essentially our meter either flows forward or backwards. And for the energy itself, we pay the same price for what we sell back to the grid as what we buy from the grid in any given month. The difference, of course, is that there are other charges on your bill, transmission, distribution, etc. On those, we pay based on the total deliveries, not on the net deliveries for the month. So everything that comes in These blue arrows, anything that's in that, we pay transmission and distribution charges on those. So here's what it's looked like for us over the last few years in our little household energy system. So in the summertime, so in the dark blue line is if we'd have just signed up for the regulated rate electricity contracts, paid the prices associated with our consumption, this would have been every monthly bill we've had since we put our solar panels in December or August of 2017 for the variable charges that are associated with energy transmission and distribution. The light blue line is what we've actually paid because of both our solar project and our ability to essentially choose what contract works best for us in which month of the year. And what you can see from this is that overall, we've saved on average about $70 a month from having this solar power system installed. And so if you want to do the back of the envelope math on this, if you can do net present values on the back of an envelope, I certainly can. I'll use my computer. But the past year, we've been at about $1,000 a year total savings, so a little better than average. But if we extended these past 4 years' returns out to the rest of the horizon of our system, we'd probably earn a financial return of about 4%. But now the question is, were my students right? So 4% is probably better than lumping down on my mortgage anyway, but what about the nerd value? And I thought I'd show you a few fun things to give you a sense of the enjoyment that I get out of having this little added part to our energy system. So the most fun I've certainly had with it, about a month after our solar system was installed, we had a solar eclipse here in Edmonton that some of you will remember. And it was fascinating to be able to sit in my basement and track the solar eclipse from literally the moment that it began. You could see the generation wheel off of our solar system, and we had an almost cloudless sky. It was great for the first half. Second half was a little more interrupted, so we didn't get a perfect curve off of it, but it was pretty close. You can also run some other experiments. So for example, this is me on Boxing Day heading out into my backyard to see how much of a difference would it make if I shoveled off or brushed off my solar panels. So I built myself a little solar panel brush and cleared them off to see what difference it would make. The answer is it probably isn't worth doing, but it's a fun little experiment, and it occupied me for a few minutes on a Boxing Day holiday. And there's a bunch of these other ones. I didn't include them all in this deck because I wanted to make sure I stayed under my time, but you can look at how wildfire smoke affects it, rainy days versus cloudy days, all sorts of different information. But generally speaking, if I add in, and I take my students' initial conclusion here, if I add in my cup of coffee a day of nerd value, which I think is probably an underestimate for how much I get out of it, they were actually pretty darn close. That would push my return to about 19%. So that's probably a good proxy for not only my ability to play with data, but my ability to use it for events like this, as well as to teach my students about the solar energy regulation and solar power systems. So I think my students did a pretty good job. So this is, I hope, a little bit of a starting point for you to think about the fact that energy systems are all around us, and one of the ones that we interact with the most on a day-to-day basis is this is the one that's in our own house or our own apartment, and how that relationship is changing to now be one where we have more of a two-way street, where technology allows us not only to be straight consumers of electricity in this case, but also producers of electricity, storers of electricity, etc. And so you'll hear more from my colleagues coming up about other parts of the larger energy system. And of course, that all fits into how I can earn dollars from my solar power system. But I think it was nice to be able to start with a small one pretty close to home, and hopefully you found this an interesting trip into the world of solar power. So thanks for the invitation, and look forward to my colleagues and to your questions.
Awesome. Thank you so much, Andrew. It was great to have that come a little bit closer to home and also learn about the economics and how we can increase our nerd value. So I'm sure there's tons of questions. Just a reminder to the audience, please feel free to use the chat to chat amongst yourself, and please enter any questions you might have into the Q&A. We'll get to all of the questions after our next 3 presentations when we go into a 30-minute panel discussion. All right, so our next speaker is Jessica Vandenberghe, who will be presenting a cradle-to-grave perspective on the oil sands. Jessica Vandenberghe, pronouns she, her, is the Assistant Dean of Engineering, Community and Culture and Industrial Professor, Indigenous Engineering. She is alumni from the Faculty of Engineering at the University of Alberta with a BSc in Chemical Engineering, Computer Process Control Co-op, and a Master's in Chemical and Mining Engineering. She has worked in the oil sands, regulatory, infrastructure, and consulting industries. She loves to downhill ski and enjoys camping with her 2 children. So please go ahead, Jessica. We're looking forward to your presentation.
Thank you so much. Andrew, if you don't mind just stopping your share screen so I can share my presentation here. Perfect, thank you. All right, thank you folks for the invitation. I'm always happy to come and chat around energy. All right, so I'm going to talk to you about energy life cycle. So my background was working in the oil sands industry for many years, but I want to start off just talking a little bit first about some of the medicine wheel teachings that I've had, because we are working here at the University of Alberta on Truth and Reconciliation, learning how to integrate Indigenous content, learning how to walk the calls to action for truth and reconciliation. And so when it comes to cycles, the medicine wheel teaches us quite a few things. So I just want to read a little bit of a passage from Black Elk Speaks. And so this is teachings from one of the elders down in the south of us here. And so what he says in chapter 17 of his book here, it says, "You have noticed that everything an Indian does is in a circle. And that is because of the power of the world always works in circles and everything tries to be round." And so it goes on to say the life of a man is a circle from childhood to childhood. And so it is with everything where power moves. And I just really want to talk about that last sentence in there. So it's the same with everything where power moves. So when we talk about energy cycles, we're really talking about spirit. We're talking about this energy that moves from one state to another. And we really need to think about that cycle and how we can be ethical, how we can be thoughtful around reclamation, how we can think about the impact of shifting and changing that energy from different states or into different forms in order to harness it for the use that we're doing, in order to really think of that whole cycle together. So again, I'm going to chat a little bit about the oil sands. So the oil sands, there's a lot of deposits around the world. Here in Alberta, we have a very large one up in the Athabasca region, so in the north. There are a couple different methods that are used to extract and refine and process this. I'm going to talk about the open pit mining that is used up there. So the oil is trapped within the sand. We know that historically, this was often used by Indigenous people for patching canoes and creating a different a type of glue, a type of different uses for within their community. But for the mining extraction industries, we were looking to harness the energy that is within the bitumen, within the oil sands. And so this whole life cycle starts from being able to dig up the oil sands. In Fort McMurray, this is a picture of the large scale operation that happens there. It moved from a bucket wheel type conveyor convention now to trucks and shovels. And so that extraction of the energy source, the material that the energy is in, whatever its natural occurring state is. From there, it is moved and it's processed. It goes through large amounts of mechanisms in order to break up the large lumps of the sand. It goes to an area where they do hot water extraction. They turn it into a slurry using high temperature waters in order to hydrotransport it to large separation vessels. And so it's within the large separation vessels where the oil floats, the heavier sand sinks. But a large portion is trapped in this middling stream where there are tiny droplets that don't quite know whether they want to float to the top or whether they want to sink to the bottom. Same with sand is often put together with the oil sand droplets. And then we have a mixture of water in between there. And so a lot of the process then is used to process that mid-lane stream in order to capture more of that bitumen that comes out of that. And so in this case, we know that the energy is within the bitumen. It's that oil product that will be later refined and upgraded into the products that we use every day. And so they're really trying to capture everything that we can from this whole system, but also being thoughtful about what we're adding to the process in order to extract that bitumen. And then how do we handle those types of products? So for that mid-lane stream, there's a lot of research into the areas of how can you extract that? Can you do that through chemical froth treatment? Is it through more mechanical means? Is it through flotation columns? Is it through different mechanisms of aeration, perhaps? Different types of way of coalescing the droplets together in order to change the chemistry, in order to extract that extra bitumen that's in there. And so from there, once all the extraction is done of the bitumen product, it goes off to the refinery. And it's in the refinery where we manipulate the properties in order to find the streams that we want. And so manipulating typically the temperature, really high temperatures, cracking those hydrocarbon chains, and in order to pull off the streams that are desirable in order to process into different products later on. And so the energy cycle, when it comes to a resource like the oil sands, goes quite a long way. So from that mining, from the extraction into the upgraders, and then from the upgraders, it's still refined even further into a variety of products that we use every day. So things like the gas for our vehicles, or perhaps it's refined to a state that's suitable for jet fuel, or it goes off to petrochemical plants in order to be converted to something like plastics or things like that. But our challenge when working with an energy life cycle, again, is not just to reach the goal of extracting that energy. It's also being thoughtful about all the byproducts that are being produced as part of this energy cycle. So what do we do with the land that was shifted? What do we do with the impact to the surrounding communities? Because we're using a large amount of water. We have a large area needed for tailings ponds. How do we move it back to restore the ecosystems and reclaim the lands, replanting natural and native plants that will take to the area? How do we handle all of that? And so the challenge with taking a natural resource through its whole energy cycle is very much not just limited to the singular pieces within the process. It's for that larger system. And that's really what we're here to talk about today, some of these systems that energy is involved in. And how do we, as professional engineers, as researchers, how do we make sure that we're making ethical decisions, that we're thoughtful in the impact that we have, not just on the other pieces within the process, but also on the environment, on the ecosystems, on the surrounding communities that are impacted downstream or upstream of these larger scale operations. That is really one of the largest challenges when it comes to being part of an energy type of resource extraction industry, is how do we handle and mitigate all those risks associated with the impact of changing and manipulating our oil sands, our energy source from state to state, and how do we take care of the pieces that come away from that we need to either restore back into the process or recycle, or somehow reclaim or somehow restore back to the natural environment. And so that is all really I wanted to share on the overview of energy life cycle from the oil sands point of view. And that's just to give you a thought, give you a start to thinking about, well, how do we do this at a very high level systems level from a natural resource all the way through to when we use it in day-to-day use. And so I'll leave it there and I'll hand it back to you, Amina. Thanks.
Great. Thank you so much, Jessica, for your very thoughtful presentation and explaining to us the life cycle of a system that we're familiar with in some aspects and thinking about the ethical considerations of a large-scale energy system. So as before, there's plenty of time to interface with your speakers, so please put your questions in the Q&A for the panel that's coming up after. So our next speaker is Dr. Pierre Mertiny, who will be discussing conflicting objectives in water resource management. Pierre, pronouns he, him, is a professor of mechanical engineering, teaching classes primarily on advanced materials and engineering design. He works on short-term energy storage solutions, specifically energy storage flywheel systems for applications such as public transit and electrical vehicle charging. He enjoys skiing and is an avid cyclist on and off road. So thanks for being here, Pierre, and please go ahead and share your presentation.
Thank you so much, Amina. So, and yeah, thank you everybody for being here today. So today I want to talk a little bit about this, an experience that I had a few years ago. Let's see if I can get my slides to work. Here we go. So a few years ago, I was invited by Greg McDermott from the University of Calgary, the Department of Geography, to join a tour up and down the Kananaskis Valley. And so, as Amina said, I'm a professor and a researcher working in energy systems. And so I thought I had a good idea what an energy system actually is. So when he told me that this is a tour about the hydropower system in the Kananaskis Valley, I thought, oh, that's really interesting. Like, I want to see that. And felt pretty confident that I will understand what is going on there. So we all know where the Kananaskis Valley is, probably, like it's just west of Calgary. You know, it's a beautiful area, and if, you know, many of you probably have been there and toured around and maybe went hiking or other activities in the mountains there. And TransAlta actually operates 4 hydro plants in this valley. So they're not easy to find, but they are there. And so they are at the upper and lower Kananaskis Lake, at the Barrier Lake, and then very close to Trans-Canada Highway in the Bow Valley. And so these 4 plants have a capacity of 54 megawatt. And if you do the math, they do actually create about 170 gigawatt hours per year of electricity, so energy, you know, over the whole year. And that kind of accounts only for like 30% like time of use of these plants. So they're not operating full capacity all year long, which, you know, I get to in a moment. For comparison, I always, like engineers, always throw these numbers around. I just kind of try to put this in perspective. So for example, TransAlta also runs a large coal and gas power plant in Wabamun, here not far from Edmonton. That facility has 800 megawatt power. So it's significantly larger. So we see this is like, you know, like this is only a 16th, if I do the math right here, the hydro plants in Kananaskis compared to this large coal-fired power plant or coal and gas-fired power plant. If in another, like, you know, if you go to renewable systems, in Pincher Creek, like one of the wind facilities that is there, the Summerview one, it's like 38 wind turbines, so it's sizable, it's not small, right? So this has about, it's like roughly similar power output, like 68 megawatt. And for comparison, like the city of Calgary, on an, you know, on an average, over the average of the year, the city of Calgary needs about 1,400 megawatt of power to operate. So this hydropower system in the Kananaskis Valley is small. It's not a massive power system, right? But it's nice. So there are the 4 hydro plants. There's one, and the first one is called the Interlakes one. That's highest up in the mountain, and then Pocatera. It's a little bit lower at the lower Kananaskis Lake, and then there's the Barrier Lake plant and the Kananaskis plant, and that's the one close to the highway number 1, the Trans-Canada Highway. So, so as an engineer, I thought like, well, that, you know, I totally understand what those are for. They're not there to generate power on a constant basis. Those are like, these power plants are there for peak power generation. So if this, you know, you probably remember those days in the summer when it was really hot and everybody had the air conditioning on, especially in the evening, and then our power grid is like humming at full steam, right? So it's we're like at full capacity. Power prices are the highest at that moment. And so having a little bit of extra capacity to buffer off this peak power is a great thing, right? So, and that's what really this power plant is, what I assumed is kind of is meant for, right? So it's providing peak power when it's needed. So based on that, I came to the conclusion that it's easy, right? It's a great thing. Nice hydropower plants. for a defined purpose, clean power, and as an engineer, I thought I had captured the whole idea about this energy system. But I was very much wrong, and I was glad that I went with somebody there on this tour who could tell me a lot of the difference and a lot of the other aspects that are part of this power system or this energy system. I don't know if you remember that day. That was in 2013, and what day was that? That was on, yeah, I don't even remember, the summer at some point, right? The major rainstorm that hit the western slopes of the Rocky Mountains. So you probably, maybe I've seen the pictures of Canmore, like Cougar Creek being completely washed out. Maybe the pictures of the Trans-Canada Highway, bridges being washed out. Or here, this is the picture at the Barrier Lake Spillway. So this is actually the Barrier Lake Power Station in the picture here, which I kind of grabbed from YouTube. You see there, that's the house where the power is actually generated. In the back of this picture, you see a little bit of a like a black kind of feature in the dike that kind of is the end of the Barrier Lake. That's actually the pipe that directs the water to the power station. You see here's all the electrical transformer and power lines on the bottom left of the picture. That's completely flooded. So there's so much water came down that time that it kind of destroyed a lot of infrastructure in the Kananaskis Valley. And TransAlta actually had a hard time saving the lake. You see with the water on the right-hand side, that's the spillway. So this is not the power, this is just the overflow. It's fully open and it kind of, so much water is coming out, it actually washed out the road that was there. And I'm pretty sure the white trucks that are up there, these are like the technicians from TransAlta. They're probably like, you know, crossing their fingers that their dike doesn't break and that the water gets out of this thing, you know, without causing too much damage. Anyway, the water went down the valley into the Bow Valley, down the Bow Valley, and it flooded Calgary. And you know, there was still the internet is full of pictures of, like you see here, the Stampede grounds, how they were like, you know, hip deep in water. Parts of downtown were flooded, and there was massive damage around the city of Calgary. So obviously now, like, it came clear to me, like, and you can still see a lot of the damage in the Kananaskis Valley, actually, if you get somebody who points it out to you, like on the golf course, for example, there. So we want to have flood mitigation. That's a big part of this, you know, water system that needs to be managed in the Kananaskis Valley. So whenever there's a rainstorm, they're hard to predict. We want to be able to catch as much water as we can, so to give us time to mitigate the flooding that will potentially come from this major rainstorm. So therefore, nowadays, Barrier Lake is actually kept almost empty. So if you go up to Barrier Lake right now, you will see a lot of gravel, little water. That lake is actually almost empty. And it really affects hydropower capacity that we can produce from that particular power station at Barrier Lake. So one constraint I didn't know, flood prevention is a big one. Then we drove up to a point on the Kananaskis River there, which is called the Widowmaker Rapids. That's what they looked like when I got there. It's very, quiet. You see this, you know, I point out to the right-hand side, there's this big rock feature there, right? So that kind of sticks out. And it makes you wonder why it's called Widowmaker Rapids, because there's definitely no rapids, and the little bit of water that trickles down there is not very like widow making kind of thing, right? So you can actually almost walk to these rock features just getting ankle deep into water. And I know we're told that this river is actually used for recreational activities, and some industry down in the Kananaskis Valley, they make their living on tourists and using that river. So TransAlta actually accommodates that several times a day. Several times a day. They're opening up their power station to create high flow events in the river. This is on the back of this picture. This is the same rock formation, and now it's truly a rapid. So they're changing the water flow from like next to nothing to like a meter or two in height. And that is primarily done for tourist reasons, so that, you know, kayakers and whitewater rafting companies and so on can have their business in this valley. So interesting. I had no idea that this was also a constraint. There's even an app for that. You can look this up on the TransAlta website when the high flow events will be, so that you as an operator of these, you can plan your tours. And here's the the Pocatera plant that kind of regulates the flow in this part of the river. You see that's the low flow event. It's the water is like really like just hiking boot deep at this point and just a trickle. And in the bottom picture, you see the water. If you look at the rock formation there, the water level rises by 1.5 meters to 2 meters, like when they actually trigger the high flow event. And those high flow events are not triggered when the city of Calgary needs energy. That would be a coincidence. These are triggered so that people can use the river. So tourism is an important one. Then we drove up to the upper and lower Kananaskis Lake. And in the background, you see the mountains that have the glaciers that feed this lake. So now one thing I didn't realize is that in lakes like these where the water is very cold, there's only a zone in the depth direction of the lake where fish actually can feed, where plants are growing. So the water is just warm enough, but it's, you know, it's still like and if they go too deep, the water is too cold and very few things grow apparently there, and fish can't feed. So if you cycle the water level too much, then this biozone that fish habitat needs is going to get destroyed. So, and actually funny thing is I have this little sign here that you can see at the shore. If you come at a low water level to the upper and lower Kananaskis Lake, you actually see things that look like island, but you can actually walk over to them on dry foot. If you come back later, you might see that the water level has risen like quite a bit, and these islands are not truly surrounded by water. So there's actually signs that if you walk out there and you don't go camping, you might not get back in a few hours later, right? So anyway, so because of the constraints that you have in the way you can cycle the water level, you cannot to protect the fish habitat there. You're also limited in the amount of hydropower you can produce at any given time. It's very interesting. And another thing I had no idea is, like, you know, we know already the impact that hydropower had. We know from historical recordings and from reports from native people who have been using this valley as their grounds for hunting and fishing, that there has been very different types of fish in that lake in the past. And so this has actually changed over the years due to the use of hydropower. And it changes the way the feeding zone or the biozone in these lakes develop. So again, and it's constrained that now TransAlta has to consider to protect the environment, the fish habitat in those lakes. So the water resource management means something much bigger than what I initially thought. I thought, okay, that we've just fill up all those lakes essentially with water and then let water run down through the hydropower stations to generate electricity when we need it. But no way, that's only a small portion of the big picture that needs to be considered when you look at this energy system. So there's flood mitigation, like the city of Calgary wants to have those lakes as empty as possible to catch flooding. You have tourism, people want to use this river for like boating and or kayaking and whitewater rafting. And you have environmental protection to adhere to, so making sure that you don't damage the fish habitat in those lakes. So overall, this has become, or is, a very complex energy system, seemingly very simple when I looked at it with my limited engineering view initially. But I learned that even something like that, like a small hydropower system, is embedded in a much, much bigger system that has a high level of complexity. And I think that's the my conclusion here. And so I'm going to pass it on to Amina again. Thank you.
Great. Thank you so much, Pierre. That was a fascinating presentation and very interesting to learn about the different perspectives beyond what we think is a perfect solution from one perspective and how much more goes into it. So our final speaker, before we go into our panel discussion, I'll remind you again to please put any questions into the Q&A, is Dr. Evan Davies, who'll be giving us a global perspective on energy systems. Evan Davies, pronouns he, him, is a professor in civil and environmental engineering, where he teaches environmental hydrology, systems modeling, and fluid mechanics courses. His research focuses on water resources planning and management, and particularly on the simulation of large-scale water and energy systems. He enjoys hiking, camping, skiing, reading, and time with his family. Thanks so much, Evan, and we'll let you share your presentation.
Great, thank you for the introduction, Amina. I'll just share my screen here. All right, so I'll talk to you now about global systems, energy, and everything else. You've already seen a little bit about the complexity that can exist within energy systems. And so you've seen that they can exist at many different scales, with sizes from residential all the way up to sectoral or regional. I'll talk about global scale systems and time that ranges from seconds or minutes all the way up to decades, where we're talking about infrastructure and changes in society. In terms of complexity, our analysis can focus on single energy types, as you've seen, or it can focus on some of the larger socioeconomic and environmental factors, or some of the loops or feedback effects of decisions. And so the question that I'll try to answer here is, what about the big picture of energy systems? Here we'll look at large-scale systems that are provincial all the way up to global in scale, and long-term, looking at the present day through to about 2100. And of course, we'll look at complex systems that comprise systems of systems that have lots and lots of feedbacks. And so to give you an idea of the sort of systems we're talking about, here's this figure on the right-hand side that shows energy systems, water, land, ecosystems, human health, transportation, and urban systems all linked together. And then we have all of these different factors within these systems and drivers of change. So then we have these big complex systems. How can we actually understand them? Well, of course, governments, businesses, and the public want to know the effects of their actions and their plans, both in the near term and in the longer term. And they have a couple of different ways of trying to figure out these effects. Of course, this is difficult with complex systems. And so some options are just to guess the answers, use a sort of gut feel. You can test your ideas on a limited scale, for example, try one thing, see what happens. You can ask the public, you can have surveys, figure out what they prefer. You can ask experts, and they'll tell you which sorts of policies are available and what their possible implications are. And then finally, we can use computer models. Now, some of you may ask, what is a computer simulation model? Well, here's a definition I like. This is from science fiction, from Isaac Asimov. And he wrote back in 1988, if you want to understand some aspect of the universe, it helps if you simplify it and include only those properties and characteristics that are essential for understanding. If you want to determine how an object drops, you don't concern yourself with whether it's new or old, is red or green, or has an odor or not. You eliminate those things and thus do not needlessly overcomplicate matters. The simplification you call a model or a simulation, and you present it either as an actual representation on a computer screen or as a mathematical relationship. Such simplified simulations make it far easier to grasp a phenomenon than it would be if we had to study the phenomenon itself. And to show you how complicated some of these models are, here's an animation of a global climate model from NASA. I won't show you the whole thing, but I'll give you an idea of what it actually looks like. Okay, and so here's 2015 through 2028. And you can see temperature patterns shifting across the planet. Okay, so this again is all from a simulation model, a global climate model. Okay, here's an alternative simulation. So these are not predictions, these are scenarios where we can see the potential implications of different decisions. Okay, so there's some output from a simulation model. And I'll go to the next slide. Okay, an alternative is what's called an integrated assessment model. These two are models of global systems. IAMs are computer models that simulate alternative futures under climate and other large-scale changes. So these models include many different global sectors. They include energy, land use, agriculture, buildings, transportation, water, climate, and emissions. And you can see there are lots of interconnections between these systems if you look at the image on the right-hand side. So we have at the left-hand side of that image, fine-scale Earth systems through large-scale Earth systems. These are the natural systems. Then we have physical systems that are affected by humanity. And then finally, we have socioeconomic systems. And so these will be things like the economics that drive some of the changes in physical systems and vice versa. So you can see there are feedbacks between all of these types of systems. Now you may ask, what can we use them for? Well, IAMs can be used to answer questions like, how might emerging technologies like photovoltaic cells or new batteries influence how energy is consumed and used? What might these changes mean for greenhouse gas emissions, air pollution, international markets for fossil fuels, and access to energy? How might changes in population, income, or technology cost alter things like crop production, energy demand, or water withdrawals? And how do changes in one region's demand for energy affect energy, water, and land in other regions? And of course, what are the effects of these changes now and potentially 100 years from now? I'll give you an example so that you can get a little bit of a grip on some of these ideas. So I'll talk about a research project that my group at the U of A is involved in. And we'll talk about here the global change analysis model. So GCAM is a well-known open source community integrated assessment model that's developed by the Joint Global Change Research Institute, or JGCRI, in College Park, Maryland. The U of A, JGCRI, and Environment and Climate Change Canada are working together to develop a 13-region, 10-province, 3-territory version of GCAM Canada for future energy scenario analysis. Our aims are to, 1, prepare GCAM Canada to support decision-making for new energy and environmental policies, identify promising national, provincial, and corporate strategies and compare different outcomes. 2, apply GCAM Canada to questions related to oil sands development, renewable energy options, and industrial development. And 3, in the longer term, apply GCAM Canada to questions related to land use, agriculture, and water resources, again at that 13-region scale, so that we can differentiate, for example, policies in British Columbia from Alberta, or Quebec from Ontario, or wherever. A little bit more information on GCAM. GCAM simulates energy, land, water, socioeconomic, and climate systems. It has 32 different regions that include Canada, the USA, China, Europe, and India, and 27 others. You can see them all here on the left-hand side. In terms of energy, it models fossil fuels, so resource production, through electric power plants and renewables. That's the energy transformation component. And then it also simulates end uses in the building, transportation, and industrial sectors. And you can see a little bit more about how that component of the model works in the bottom left-hand side of this image. It also simulates the growth of food, feed, and livestock, a bunch of different crop types that are used for feeding people as well as feeding animals. It simulates also water, so both the supply or the hydrology at a river basin scale, and you can see all of the different river basins that are represented over here on the left-hand side again, as well as the demands for agriculture, for industry and energy production, and for domestic purposes within households. It also simulates climate and emissions, so the releases of greenhouse gases and corresponding changes in temperature into the future under different scenarios of releases. It simulates economics, and so GCAM solves for market prices in energy, agriculture, and water sectors that balance the supplies of of energy sources, for example, with the demands for all of these different markets. And it runs at 5-year time steps from the current time, 2015-ish, 2020 to 2100. So it is a very complicated model, of course. In terms of sample applications, I'll talk to you about a project that we recently did for hydropower production. This was conducted by a master's student and some colleagues from JIGCRE. The master's student is Evan Arbuckle, and I think he's on the meeting right now. In terms of context, hydropower produces 60% of Canadian electricity, and the capacity is expanding. However, at the same time, we have a problem, which is that several large hydropower projects under development have seen significant cost overruns. So you may have heard of Muskrat Falls in Newfoundland and Labrador, Kiask in Manitoba, and Site C in British Columbia. These are not unique to Canada. This is actually a very common problem. Such cost overruns are actually common in many places in the world. And so what we did was we made some changes to modeling hydropower in GCAM. We made it part of the overall energy system. Historically in GCAM, hydropower has been modeled as what's called a fixed output. That means that we assign a certain amount of energy production from hydropower over the time period from 2015 through to 2100, and that just happens in the model. It doesn't respond to markets. So hydroelectric generation used to be preset for each scenario. We could have higher levels or smaller levels, but it wasn't responsive to markets. There would be no expansion of hydropower if hydropower was cheap relative to coal, for example. Further, hydropower did not actually affect a region's modeled electricity price. The electricity price came from thermal power, so coal, natural gas, also from some renewable sources. Okay, so we made some pretty significant changes. And so our aim for this study was to explore hydropower capacity expansions and cost overruns. And our research questions were, how does capturing the cost of hydropower capacity expansion affect its share of Canada's electricity generation over time? So if, for example, we're looking at net zero energy in Canada, or zero emissions into the future by 2050, for example, maybe some of our electricity should actually come from hydropower, which is emissions free. So then we were looking at an exploration of changes in the electricity system that were caused by endogenous hydro, so that hydropower capacity could expand given some signals from policy, from government. Secondly, how does endogenous modeling of hydropower affect electrification of end-use sectors? So the demand for electricity in industry, in buildings, in transportation, electric vehicles, and so on. And here we were looking at the ripple effects of changing electricity prices through the energy system and onto electricity users. And third, how does inclusion of historically observed cost overruns for Canadian hydropower plants affect electricity production and end-use sectors? And so if you model hydropower as unreasonably cheap, for example, that will have implications for future expansion in hydropower as simulated in this model, right? And so here we were looking at the effects of greater realism in hydropower costs on Canadian energy systems. This is a little screenshot of the paper in case you're interested in seeing more about this. Okay, and I should mention that these are our views, not the views of the Government of Canada. Okay, so here are some results, at least briefly. Our first question was, what happens if we have endogenous hydro? And what we found was endogenous hydro becomes a larger part of the electricity mix. So here we have the historical simulation running from 2010 through 2050. You can see that hydro is important. It's about 60% of the total mix, and it reaches 417 terawatt hours for Canada. If we model hydropower endogenously, though, and so its expansion is determined by model forces, by economic forces, rather than by preset trends, it reaches a reasonably significantly larger number here. So we're up to almost 500 terawatt hours from 417. And you can see it sort of crowds out some of the other energy sources, electricity sources. Our second question was, what happens if we include cost overruns? And it does what you would expect. So if we include cost overruns, they do reduce hydropower capacity increases. And so here is the sort of experimental approach we took in this table on the left-hand side. We simulated effects of various levels of cost overruns, from sort of moderate increases in costs all the way up to extreme increases in costs, 100% more expensive. And we looked at the effects of various different technologies. So what if we only had the cost overruns for hydropower? And what happens if we include cost overruns for other technologies that often experience cost overruns as well, like nuclear power plants, or some of these newer ones like carbon capture and storage, or integrated gasification combined cycle, which is a coal-fired technology. Okay, and here's what we found. So here's the endogenous hydro as the first image here. And you can see how we're explaining the range of cost overruns and which technologies are affected in green and blue, respectively. Okay, and so you can see in terms of results, cost overruns decreased hydropower. Okay, and so you can see that comparing 495 versus 464 versus 404 versus 376. And you can see that as we incorporated more technologies in these cost overruns, we crowded out, or rather, hydro became relatively more preferable as other technologies also experience cost overruns. Okay, the other interesting thing that happened was cost overruns also decreased electricity generation. So hydro became more expensive, that drove up electricity costs. And so rather than electrify in industry and transportation and households and buildings, instead people just continued to burn natural gas in their furnaces at home, or they burned coal in industrial processes, and so on. Okay, so we got the sorts of results we expected, but it's nice to be able to see the future trajectories under these different scenarios. In conclusion then, you can see that energy systems interact with a huge number of other systems. And so you've seen a couple of examples now of hydropower. We have science and engineering. We have the electricity system, so infrastructure as well. We have economics playing a role, and we have society. The other thing I hope I've shown you is that we have tools to analyze even these really complex systems. So we can explore alternative energy futures with computer models. Models like GCAN help us to weigh our options, and we can see local and global effects of available energy, water, land use, and climate policy choices now and all the way out to 2100. Okay, thanks for your attention.
Great, thanks so much, Evan, for your presentation and explaining to us how we can handle giant systems, even systems of systems, and project this to understand potential future realities. So before we break into our panel, please put any questions you have into the Q&A. And I just want to give a quick summary of everything that we learned from our speakers. Well, not every, quick summary of what we learned from our speakers today. So we started off building from a small scale system that could be in your house, solar power, from Andrew Leach explained to us the economics of this, and also how we can get a little bit nerdier through installing solar panels. We built up to a larger system and understanding a life cycle of the oil sands, starting from the important role that oil sands have played in different communities over time, how it impacts our life, and how we have important ethical considerations when we look at these large scale systems. Pierre gave us a very interesting overview on different conflicting perspectives. He called it seemingly simple, but actually complex, understanding how there's so many different things that can go into a single engineering technology and the different narratives and desires of different communities. And then Evan was showing us how we can put all of this into a computer model and consider what might happen in the future and which impacts in the system can play out in different ways. So thinking about that, we invite you to put any more questions you might have to the panel into the chat. And we're now going to go into our panel discussion. So you should see, I think, all 5 of us up on the screen. And I'll open with a question. I'm going to start with directing this to Pierre, but with how complex energy systems are, how do we avoid getting too focused on either the forest or the trees? How can we balance both?
That's a good question. I wish I would have an answer. When I actually I had a question for Evan, like, you know, like you can only model what you know, right? So, and so this is sometimes I think the challenge, like we're, you know, we need to know all these trees to understand the forest, right? But the trees often stand in our way to actually see the bigger picture, right? So, and I think this is, like, I think the biggest part of this is actually to work in an interdisciplinary team, right? A team that captures many different aspects of this and have these communication between the different experts of, you know, levels of expertise, which is not easy because all of these engineers speak a somewhat different language than economists, and economists speak a little bit of a different language than, say, environmentalists, right? So it's like everybody has their own little thing and we need to understand each other better. And I think that we're working on this, but there's still a lot of ground that needs to be covered. And I mean, Jessica brought in a very important perspective, like also we coming with our own cultural background and thinking, right? Which often limits us in our understanding of how the world functions. So long story short, I think, you know, when it comes to the forest of the trees, we need a lot of people to walk around and identify all these trees for us to actually capture the bigger picture, right? And so this whole lecture series, maybe that's one of the reasons why we're having it. So we want people to be able to engage in these discussions from different perspectives, not just from, you know, I know how to design a power plant, but also like, you know, how does it affect many, many other areas?
Great, thank you, Pierre. And I'm wondering, related to that, Jessica, you've worked in the oil sands industry and in different parts of the industry. How have you seen this balanced, and what are your perspective on being able to communicate with different expertise in different groups?
100%, just to build off what Pierre was saying, that when it comes to engineering design and engineering projects and engineering operations and maintenance and reclamation, it is important to have in those beginning stages at the planning table, at the risk assessment stage, a lot of diverse perspectives and people able to navigate and represent the voices who aren't at the table. So expertise around the environmental impact, the ecosystem impact, in the case of the oil sands that border on a lot of First Nations and Métis Nations up there, making sure to have that Indigenous voice at the table, thinking through having the technologists and the operators, the mine folk, as well as the upstream folks at the table as well. I know we can't have everybody, of course, at a table. Decision making would become impossible, but making sure that you have people with multiple perspectives and have a thorough review process as part of that. And so really, really being able to communicate with each other and think about who can wear multiple hats at that table when you're making your plans and doing your risk assessments and doing all that planning.
Thank you, Jessica. Does anyone want to follow up on that, or I have I guess, go ahead, Evan.
Yeah, I was just going to say, your question about forest and trees is a good one. The approach you want to take often depends on what the question is. And so there is no one solution to all our problems, right? We need to apply the right tools. So whether those are simulation models or economic analyses or stakeholder interviews or whatever, there are many different approaches we can apply. But there is a generic approach that we can use for dealing with these kinds of really complex problems, and it's called the systems approach. And so it does actually give you a set of sort of generic steps that you should follow for dealing with any of these really complicated problems. And one of the first things it asks you to do is define the problem, because that's actually a great deal more complicated than you think it is. And so, you know, that's where stakeholders can help, because they can help you to figure out what the actual problem is. And then the next thing you try to figure out is what the boundaries are. What do I care about and what do I exclude? And you can see with something like climate change, historically, we've excluded a whole lot. And so when we talk about climate change now, what we're trying to do is internalize the climate problem within our decision making so that we draw our boundaries a little bit broader.
Thank you. Yeah, it's a really good point. And the systems can become very big and seem very overwhelming, especially when we think about climate change. And then there's also things we can do, like Andrew showed us, of closer to home and ways that you can have your own energy system or that more people can get involved. I wonder, Andrew, what you think about the role of individuals in this could be, or what you could say from that perspective.
Yeah, I think there's a mix here. There's things like problems like climate change or other societal problems are not going to be solved by just individuals, and they're not going to be solved by volunteerism. Both of these things contribute to it, but they're not going to get the job done alone. So take even my little energy system. What did I need in order to make that work? I needed an Alberta government policy that said I was allowed to do it. I needed a municipal utility that was willing to hook me up. I needed there to be installers who were available, who had enough business to make a viable business installing solar power in the community. And I needed my neighbors not to plant trees in the way of my garage. So there's local things, there's policy things, et cetera, that all tie together. And there was a great article in the New York Times this week, or a week ago, about a group that had put a $30,000 solar system on their roof, and their local utility wouldn't hook them up because there's too much solar already in the area. And I know Peter Mercilik, who's, I think I saw him on the call earlier, has done some similar work for Edmonton. And so we're going to be in a situation where you live might determine whether you get a permit to do this little thing that I did. Or whether you can get an electric vehicle or those sorts of things. So individual stuff works, but you can't, I'm not going to be able to string a new power line to my house to make my solar system work or put in a new transformer or anything without broader collaboration.
That's a great point. And I actually see a question in the chat that I think is getting to what we're talking about, which is we need to work together as a group. There's a collective interest here. But how do we get everyone on the same page? What are the kinds of incentives that you can use maybe to get this collaborative effort to address grand challenge problems? So I don't know if someone wants to volunteer, maybe Jessica, if you'd like to answer that.
Sure, yeah, for sure, definitely. Working with different diverse perspectives is always an art sometimes in terms of approach. Everyone has a different communication style. Everyone's coming with a different amount of unconscious bias. Folks are coming from different lived experiences that they bring to the table, and there's huge value in that. But at times, sometimes there is frustration as well, trying to convey what your perspective is and the reasoning behind it. And so taking the time to really think through, I like Evan's approach that he mentioned around really drawing those boundaries, drawing those assumptions, using the same language, building a very safe, ethical environment so people are free to bring up their ideas, as well as speak from a place where it is really active listening. And this is so important. I know the elders teach us a lot about the humility teaching, about really those circles, sharing circle type style meetings where we can create that space so people can share their ideas. They're not, and rather than being criticized or being dismissed right away, that thought be put into those ideas, whether they have pieces that are feasible, that fit, that we can all bring it all together. Of course, we always have to balance that against the needs that we're working in this world against, things like time, money, cost, resources, all of that. And finding the right balance there so that we can build those really safe, respectful environments.
Thank you so much, Jessica. And that makes me think of Pierre's presentation as he was showing us how this is working together in the Kananaskis Valley. I wonder, Pierre, if you can talk about how you saw in that system, and then maybe in different scenarios, how you can see those perspectives come together.
Yeah, so Kananaskis Valley is it's a microcosm, right? So it seemed like it's a small energy generation facility. From the outside, like, you know, if you're far away, it looks like a great idea to create electricity, right? And I just showed you, this thing is only used 36% of the year, like really to generate electricity. And a lot of this is like, not even produced at the right time where it would make most sense, right? So, but if you actually live there and you make, for example, the tour operators make their living with that river, right? Or if you are interested in the environmental protection of this area. So I always circle back to the same kind of, I think the discourse is the most important part of this thing. So we can only model what we understand and what impact it has. And another challenge is like sometimes putting value on, like putting like, all these models, and Evan, you can correct me if I'm wrong, but all of these models need numbers. So how do you measure like the healthiness of the upper Kananaskis Lake in terms of the fish habitat? What dollar value do you put on that or so, right? How do you measure that? Another interesting thing, I had a couple of years ago, I gave a talk in Lethbridge on energy storage, and I brought up like the comment that it's a great area down there for wind energy, right? And so I thought like that went over like a lead balloon. I had people in the group in the audience that were from the I think it's like the Prairie Grassland Protection Group or so, and they're like, no, we don't like wind turbines here because it does definitely interrupt the natural landscape kind of thing, right? So putting up those wind turbines, and I don't live there. I don't have to live with the wind turbines. I don't see them, right? So, and I'm originally from Germany, and I know how now people in like Germany is like always seen as this like the a great place for generating wind power because there are wind turbines everywhere. But there's a lot of backlash in society about like people don't like them to be at certain places, right? There's environmental groups who actually are against wind power in the North Sea, right? Because it interferes with bird migration and other things. So it is the discourse and gathering information, finding ways of actually quantifying the impact that certain decisions have is a real challenge. And I think there's lots that we still have to do a lot of things on that because not everything can be expressed in, gigawatt or dollars, right? So it's, and so, yeah, I think this is a difficult decision to make, and I don't have a solution. I'm actually part of this group to learn. That's kind of like my main part here.
Evan, please go ahead.
Yeah, in answer to what Pierre was saying, obviously that's a real problem with simulation models and with science in general, which is that we often try to refine what we already know rather than trying to explore brand new things. There are different approaches you can take to include some of the qualitative aspects. A methodology that I use in my own research is called system dynamics modeling, which allows you to do some more qualitative work than you can do with a lot of simulation modeling. That said, it's not perfect, and it's very hard to quantify some aspects like human health, for example, or environmental health. And so that brings me to the last point, I suppose, which is that typically simulation models, optimization models, and so on aren't used to make the decisions. What they're used for is to inform the decisions. And so you have to be very careful when you use any model that you don't use it as an oracle. It's not the answer, it's not divine. What it can do is give you a more informed analysis, a more informed understanding of what the problem is and what the repercussions are of different courses of action. So you have to be very careful. That's one of the things I stress to my students is don't think that the model is telling you the answer. What it's doing is giving you information that you can take into account as you make your own decisions.
Yeah, that's a really important point. And also with what Jessica was telling us about, when we're bringing in more people and more diverse perspectives, sometimes that needs to also shift the way of thinking that we've had in the past so we can encompass what is also very important and has been missed. So that leads me to another question that came in of not all people are equally impacted by an energy system, whether in the oil sands or elsewhere. How do we negotiate the differential impact where the people most hurt by something might not see the benefit? So I wonder, Andrew, if you could speak to that.
Yeah, I think there's a lot of questions of equity that come up with any energy system. So from one as small as my local solar system up through the oil sands to global and national questions of climate change. I mean, we're seeing that play out in the province constantly with the premier arguing for what should be federal versus provincial decision making, with these questions of, you know, what share of emissions should Alberta be entitled to or be able to claim, how much of the oil sands should be. So all of these questions have equity and burden sharing attributes to them. And then of course local ones, there are going to be people who are affected by the downstream impacts of development in a very disproportionate way. One of the questions I often ask my students, and I've done so this year, is just as a challenge question to say, do you think we would have developed the oil sands in the same way if they'd have been upstream of Calgary on the Bow or upstream of Edmonton on the Saskatchewan, as opposed to where they are located in downstream of Fort McMurray, effectively on the Athabasca? And that puts very disproportionate impacts on those further downstream populations. But in that case, it's a smaller number of people with arguably less influence over our policy. So I think those are challenges that we know well. You know, I think how do you deal with it? The first thing is information. And we've seen it, I'll use one example, carbon pricing, right? Getting out front and saying, this is the distributional impact. And importantly, not getting caught up in the averages, remembering that averages hide a lot of information. So one thing that I've seen, and I'll wrap up with this, I've seen a lot of my colleagues be content to say, you know, look, 80% or 75% or what have you of Canadians are made better off by the carbon price and rebate combined. And what that means is that most individuals at lower incomes are probably made better off, but not all. And there are going to be people, and so delving into that, you know, who within this group, even digging deeper, pushing further into the information and making sure that it's out there and in front of decision makers before they make the decisions, and then tracked all the way along is crucial.
Yeah, thank you, Andrew, for those points. And that leads me kind of to a thought and also to a follow-up question here about how often do we need to reassess these inputs to a system? So Evan, you're modeling very complex systems. How do you prioritize which parts of the model you're going to include, which parts of the system you're going to include in the model? And then how often do you need to be getting new inputs? So for example, in a bad year for fish populations in the Kananaskis, or environmental protection will be more heavily weighted. What kind of responsiveness do we need built in as well?
It really depends on the question, right? So what we can use GCAM for is long-term projections, and it simplifies a lot. As an example, the electricity sector in each of the provinces is represented as a number, essentially. So we're not looking at where those specific power plants are or even how many power plants there are. We're just looking at the total capacity of coal production versus natural gas versus hydroelectric. If you look at some other models, they approach the problem really differently. They're interested in the difference between base load and peaking, which is a sub-daily time step. And so they'll be concerned with where the specific plants are and how much electricity they can dispatch at short notice. For GCAM, you know, if we decide in Alberta that we need more coal-fired power plants, GCAM can add an additional 10 megawatts. In reality, that would never be done. You know, you wouldn't build a 10 megawatt plant, you would build an 800 megawatt plant. So each of these models has their own assumptions, each of them has their own simplifications, and they can only be used for certain things. And so if I want to know about future projections of stream flow, for example, I would use a hydrological model. If I wanted to look at energy dispatch within Canada, I certainly wouldn't use GCAM. But if I want to look at the sort of larger implications of energy and how that affects land use, because we could grow biofuels, for example, and we can put ethanol in our gasoline for our internal combustion engine cars. I can do that with GCAM because it does the agriculture as well as the energy, as well as the water requirement for that agricultural production. So I guess the answer is it really depends.
Right.
You know, what is the question and what is the right tool to get that answer?
That's very fair. And so now I'm wondering about some of those things you were saying are not captured in or not the focus of GCAM, which is like energy storage systems. And Pierre, that's your specialty. How do you see that? What do you see the role of small scale energy storage systems being in this discussion?
Well, that's an interesting one, and I'm trying to understand that. It very depends on many factors again. So if you go to without going into too much detail, if you have a lot of renewable systems on generating power, so wind and solar, and we don't have a lot of other means of generating electricity without carbon emissions, so like hydropower would be one of those, but in Alberta we're not really blessed with a lot of hydropower. So but there are options for that, right? So we can decide, okay, maybe we want to work better together with our friends to the west in British Columbia, which has a lot of hydropower, right? So if we would have an integrated power market with BC, that would change the situation quite a bit. But we can also think about local storage in Alberta so that we can store energy here to get through those moments when the wind doesn't blow and the sun doesn't shine. They will definitely happen, as Andrew, I think, can attest to, right? So, so those moments, we have to have enough power in place. And I think people are not willing to accept being limited in power. I mean, it's an interesting fact too. Like, I think North Americans are quite, we like our freedoms, and we like to turn on, for example, our air conditioning when I feel like I want to have it cool in my house. But for most people, it probably doesn't matter that the power provider is actually sending out an email or a message or bringing a news item into the media saying, we are running at full capacity, please turn off your air conditioner, right? People are like, well, no, it's hot, I need this thing on, right? So, and if you think about energy storage, that is the different means or different types of energy storage, like big energy storage systems that are run by utilities, or your energy storage at home. I had a lot of discussion with folks like, if you have electric cars, for example, you can use electric cars as a means of energy storage for the electrical grid. Like in Japan, that's actually one of the systems that's being considered. Would this work in Alberta? Would I be willing to have my car so at the mercy of the utility at any given time, or would I have to be always opt in? And would I actually do this if I get a message on my app on my phone says, do you want your car being like serving to provide power at this moment? Or would I say, nah, no, I better not. Maybe I want to drive somewhere tonight. So it's a very interesting question. And I think I'm always coming back to this. I'm sorry that I don't have a definite answer. It's like, to make these decisions, we either you do the draconian approach, you say, that's the way it is, or you incentivize them somehow from a policy point of view. Say, what, you get money for it, or we force people to, somebody has to pay for it in the end, or we let market forces work this out. But there's a cost to all of this. Sometimes it might be the time that it takes to sort it out. Sometimes it might be environmental costs that it takes to, or it's the freedoms that we pay for it. But I don't think we get any of this for free. So energy storage is one of those. There's no silver bullet, right? So something has to give. It's cost, freedom, and somehow we have to pay for it, right? So, or like environmental impact that we kind of have to live with, right? So these are very difficult decisions. But yeah, I think in energy storage, essentially the technologies that we need are there. So this is one of those things where I would say, yeah, we're fine tuning them and we're trying to find better ways, but in general, we could make it work. It's just, we don't really how. Like, that's the thing, like how, in terms of how do we implement it, right? So who's going to pay the bill? Who's going to be really on the hook for it? And who do we ask to make these decisions, right? And that's one of the big challenges.
I think, Andrew, I'd love to hear what you have to say about that as well.
Well, I was going to say, Pierre's caught on to what was always the bonus question of my assignment, which is, if I wanted to be off the grid as opposed to just a grid-connected solar system, what would it take? And you really end up, you see very plainly, and I talked about the nerd value of solar power, but this is where you really do see how big those challenges are, is that, I can smooth out my solar gen over the course of a day with something like a Tesla Powerwall, and that does a good job at that. And it wouldn't pay for itself in Alberta's market, but it, at least it would allow me to rely more on my solar power system. But if I actually wanted to be off the grid and not change my behavior, I would need hundreds of Tesla Powerwalls to maintain the level of electricity use we have, even with our solar power system that is effectively net zero through the year. We are very short power in the cold months of November and very long in May, June, July. And so we'd be buying very expensive technology that we'd essentially only be cycling once per year. We'd be filling up a battery with solar power in May and essentially setting it aside until December when we'd use it. And it would be a shipping container full of batteries to do it. And so it's if you want to maintain using your dryer and using your all of your appliances and all of these sorts of things, it's very hard to do. And scale that up to a grid level, I think you get a sense of how big those challenges are. And I think Pierre did a good job of highlighting some of the opportunities for collaboration, but also this question of, what are we willing to accept in terms of either changes in our habits, changes in reliability, et cetera, in the electricity system. The one thing, though, that I put my hand up for something slightly different, which is the role of information in this. And one of our future webinars is going to talk about literacy, energy literacy, et cetera, I think. But it's interesting to me how the blame gets placed on things which are new or things which are different. So the Texas blackout is one example. The storyline that got a lot of attention was this is because Texas relied on wind and solar, and the implication that somehow all of these grid engineers in Texas had never occurred to them until this very moment that the sun doesn't always shine and the wind doesn't always blow. And that's not true. What actually happened was it hadn't occurred to them how much of their natural gas infrastructure wasn't winterized. And we see this same dynamic happen in Alberta a lot in the peak summer days. It's not just that people are running their air conditioners, it's that the river water that we rely on for cooling some of our fossil fuel power plants is now warm and can't do that as efficiently as it otherwise would. And often it's the coal plants that go offline during our summer peak periods as well. So, the narrative that gets crafted around, well, it's just dealing with when the wind doesn't blow or the sun doesn't shine is not fair. It's also dealing with when our fossil fuel plants can't generate, when our interties aren't available, and when the wind doesn't blow and when the sun doesn't shine, and dealing with the points when all of those happen together. That is the challenge.
Awesome. Thank you so much, Andrew. And so we're just at the end of our time. I'll remind everyone to please fill out the webinar link. And so you'll just a survey about future events. And you had a perfect plug to upcoming webinars. And just to wrap up, maybe if each person could go through and tell us what you think the single most pressing issue facing us with the energy transition is. So we'll start with Evan and Pierre, Jessica, and Andrew.
Just one, eh? I would say that our biggest problem is that we have a lot of fossil fuel fired power plants that have long lifespans, and our replacement technologies are renewables, which have intermittency problems. I'm not sure that's exactly the largest problem, but it's a big one.
Oh, am I next? I wasn't sure. So
You're next. Yeah, Pierre,
I'm
go ahead.
next. So I would say the biggest challenge that I see, and I think that's the one that why we have this lecture series here, this seminar series, is we need a broader education on the topic of energy. So that goes through, like, you know, even the experts, like, you know, folks that are on this call consider ourselves somewhat experts, but there's still a lot of things we have to learn. But also, you know, the population at large, right? So we need to have this discourse so that also we can make informed decisions and informed elections, right? So this is something, I think there's a big gap between what the challenges are and what the general knowledge is out there to actually make informed decisions and what it means. And I think if we don't have this knowledge and we don't have this information, we will not make the right decisions, right? So as a collective that we actually can say in the end, yeah, okay, we signed up for that. We wanted this as a decision as a society, whatever the definition of our society is, like global, local, and all the way down to Kananaskis Valley, right? So I think this is the biggest challenge. And I think we're, as educators, we have to step up our game there a little bit.
Just to build off of that, I agree. One of the biggest issues, of course, is getting the buy-in from the general population and making sure that it's not misinformation or opinion, and it's actually grounded in science and math and fact. And the important part of educating the general population around the need for this energy transition is in order to ensure that the governments and the regulators put in place the right frameworks and policies in order to make sure that we do keep the public safe as these things transition, as we work towards moving to a different type of energy future, that those frameworks are in place and they're thought about in an equitable way. The government, of course, and the regulators are swayed by industry influence. So ensuring that industry is making awareness and outreach and education a part of their grant proposals and part of the work that's being done is crucial to this. Thanks.
I'm going to say people, and I mean that in a couple of different ways. I think the disruption to employment's way of life, local communities, et cetera, that come from both the energy transition, the people who are left to clean up what's left behind from some of the legacy assets or left with those. And then I think also globally, we're going to see, we tend to get stuck in our models and think about nice orderly transitions with global carbon prices, bringing on new innovations in ways that, you know, aggregate up all of the local disruption. And we're seeing some local disruption here. And I think we're going to see a lot more of that, a lot more of the disproportionate impact. So to me, it's people. It's figuring out how to make our policies work for people.
Thank you so much to all of you for teaching us about energy systems today and for this wonderful discussion. And thank you to the Energy Systems Signature Area for hosting this webinar and to everyone who attended. It was great to have you all here, and keep an eye out for our next webinar that'll be coming up shortly. So I wish you all a good evening and see you soon.
And thank you to you, Amina, for excellent moderation.
Thank you.